So we are exploring the magnetic field in the region near a black hole, and that magnetic field is brought to the black hole in some way through the accretion disk. And we'll then look at the equations for the accretion disk and try to figure out the radial velocity. Right, so the accretion disk is material rotating around the black hole like this. It forms this flattened structure, but this material slowly migrates inwards and grows the black hole, and it will drag the magnetic field with it. And we identified the following equation for how the magnetic field is changing in time that involves a term that we call the dragging term that looks like that. And we'll explore this in a little more detail. But here is that velocity term. And so if we have a velocity that is inward toward the black hole, this somehow is involved in affecting the way the magnetic field changes in time. So we'll explore that term in a little more detail. And then we saw that there's another term here. We used empty space mu naught times del squared of the magnetic field. And this term we call the diffusion term. We'll look at this in more detail and see that it kind of represents weakening of the magnetic field. And so these two terms sort of compete with each other. A very important quantity is the magnetic flux, which is actually defined as the integral of the magnetic field over a surface, and in particular the magnetic flux on the black hole. So there's a surface there just outside the black hole, fixed value of r, and we integrate over that surface and we evaluate the magnetic flux, and the jet power will depend on this magnetic flux. But this is clearly a non-curved space-time, right? We're not dealing with general relativity here. So maybe as we get close to the black hole, we need to be more careful here and evaluate this in terms of the curved space-time formalism. So near a black hole, let's look at what this, the equations that then reduce to this are, right, Maxwell's equations, the Faraday tensor. We've seen these equations times JA, and the current density 4 vector can be written like this, where this is the velocity 1 form. And so we combine these equations into something like this. And then we want to explore something like this. Ultimately, we want the magnetic flux on the black hole. That's going to require that we break this up into the 4 vector potential. So it's derivatives of the 4 vector potential. So it looks like that. And the magnetic flux, so the B flux, ends up being an integral over some surface of these dA quantity. Well, it's 2 pi a phi. We'll look at this more closely, but a phi is the fourth component of the vector potential. Well, this is the one form, a mu, or let's just use a subscript, B or C or whatever. So it's A or A3, want to call it A3, in T, R, theta, phi coordinates, that would be A3. And so we would be looking at a space-time boundary where R, theta, and time are constant, and then we're integrating in phi. So that's where the 2 pi comes in. Okay, so we want to look a little more closely at this term, right, in the non-GR regime. Oops, what am I doing here? This is a V. So we're looking at this term. So it's the curl of V cross B. And this, we said, involves the velocity and the magnetic field, and essentially it's telling us about how the magnetic field changes in time, right? So dB by dt is changing in time in a way that depends on whether the plasma in the accretion disk is bringing magnetic field there. So V sort of brings or drags B field. And so we could make a drawing that looks like this. So here is the disk. Let's just make the drawing maybe for the part on the right. So there's magnetic field out here, and it kind of will have a structure that looks like that. It sort of threads, right? There are currents here, magnetic field loops around, and then the plasma is moving inward, so it kind of pulls these magnetic field lines inward with it. And we'll look at the equations again for the accretion disk, and there's this radial inflow velocity component that in here essentially pulls the magnetic field with it. And so that increases the magnetic field in some region. And then let's get another sheet and make a drawing of the accretion disk again. Let's just make one side, and let's make a little bit more complicated structure. Let's say something like that. Magnetic field looks like that. And this tangling up of the magnetic field goes into these spatial derivatives of this term. And so the more tangled up the field is, the greater this term, and we'll end up getting a negative sign. And so these spatial derivatives are negative, and this gives us a what's called a diffusion of B, and so the magnetic field sort of decreases as a result of that. We can sort of think of this term and the diffusion as doing something here that averages out the field and produces something smoother. It looks like that, but the magnetic field has decreased as a result of that. And that energy, so there's some energy in the magnetic field as a result of this, and now goes somewhere else. It goes into particles that are there. And energy goes from magnetic field to particles, kinetic energy or something like that. We'll look at that in more detail. And especially, let's go back to the equation we started with. This equation here, we'll look at some of the moves that astrophysicists make. In particular, we mentioned the idea that this term, the conductivity, becomes very large, effectively that you can consider it infinite. And so basically this term kind of goes away. We'll look at what this means, that the magnetic field just gets dragged wherever the plasma goes. This is called the flux freezing condition. We'll look at what happens in simulations where they ignore this term and get a sense of whether or not we can really say that we are representing accurately the real world.